Modern web users expect seamless, state-heavy applications, social media feeds, interactive maps, streaming video, all functioning instantly. Yet we demand this performance from a protocol constrained by the rigid mechanics of static text retrieval. When the Hypertext Transfer Protocol was originally developed in the early 1990s, it had a single specific purpose: fetching basic text documents over the internet. Look at this protocol stack. HTTP is an application layer protocol. It handles the logic of requesting and serving web pages, but it relies entirely on TCP at the transport layer to guarantee the delivery of that data across the network. The defining constraint of HTTP is that it is strictly stateless. An HTTP server retains zero memory of past client requests. Once a file is sent, the server completely forgets the transaction ever happened. To see how this breaks down under modern loads, consider a standard network stress test. A client requests a single base HTML file that references exactly 10 distinct JPEG images. Because the server forgets the client the moment that first HTML file is delivered, the browser must initiate 10 new, distinct requests for those remaining images. 11 objects total means 11 isolated HTTP requests. This mechanical rigidity places massive stress on the underlying network. To achieve the speeds we expect today, the transport mechanics beneath HTTP had to evolve. We can map this evolution across 5 areas: connections, message formats, state, caching, and framing. To calculate the cost of those 11 isolated requests, we use round-trip time, or RTT. This is the exact duration required for a small packet of data to travel from the client to the server and back again. This timing diagram illustrates a non-persistent HTTP connection. To fetch a single object, the client must first establish a brand new TCP connection. That requires a 3-way handshake, consuming 1 full RTT. Only then can the client send its HTTP request and receive the file, which consumes a second RTT. The mathematical penalty is absolute. Every single requested object costs exactly 2 RTTs, plus the actual transmission time required to push the file's data across the wire. Apply this to our HTML file and 10 JPEGs. If we open and close a distinct TCP connection for each object, we multiply that process by 11. The latency compounds, creating massive delays before the page fully renders. To eliminate this connection overhead, HTTP 1.1 introduced an architectural fix known as persistent connections. In this updated model, the server leaves the TCP connection open after sending its initial response. The established transport link between client and server is preserved. This open link enables pipelining. The client can fire multiple back-to-back HTTP requests into the connection without waiting for individual replies, completely bypassing the need to perform a new TCP handshake for every JPEG. By utilizing persistent connections, web performance is no longer bottlenecked by the repetitive overhead of TCP setup. The limiting factor becomes the raw bandwidth and transmission efficiency of the link itself. Over these TCP connections, clients and servers coordinate by exchanging plain text ASCII messages. What you see here is a standard HTTP GET request, exactly as it is transmitted. The message begins with the request line, which explicitly specifies the method being used, in this case GET, along with the specific URL path of the object and the HTTP version running on the client. Below that are the header lines, providing metadata like the hostname and the user agent browser type. Notice the space at the bottom. For a GET request, the entity body remains completely empty, as the client is only asking for data, not uploading it. The server receives this and replies with an HTTP response message, which uses a mirrored structure. It starts with a status line. This instantly communicates the outcome of the request through the protocol version and a status code, like 200 OK, meaning the object was successfully found. Next are the response headers, which provide critical details like the last modified date and the content length. Finally, we reach the entity body, which actually contains the raw byte data of the requested file. These message semantics provide strict, clear communication. But look closely at the data fields. There is absolutely no mechanism here for the server to recognize a user from one GET request to the next. Because HTTP is inherently stateless, the server treats every incoming message as a completely anonymous event. If an application needs a shopping cart or a user login, the protocol itself cannot help. This forces engineers to inject state externally. They rely on cookies, a 4-component tracking architecture designed to connect isolated requests. Here is how the 4 quadrants interact. Component 1 operates at the server. When a new user makes a request, the backend database generates a unique identification number for them. Component 2 is the delivery. The server replies but injects a specific set cookie header into the HTTP response message, embedding that unique ID. Component 3 happens locally. The user's browser extracts this ID and writes it into a hidden cookie file managed on their own machine. Component 4 executes the tracking. For all future transactions with that specific domain, the browser automatically modifies its HTTP request message to include a cookie header carrying that exact ID back to the server. By forcing the client to self-report an identification number on every single transmission, engineers successfully grafted a continuous session layer over a protocol that was built to forget. Even with persistent connections and cookies, physical distance matters. Sending a request halfway across the globe to an origin server incurs inevitable RTT delays. To mitigate this, institutions deploy a proxy server, or web cache, directly inside their local network. Instead of waiting for data to travel across a congested internet access link, a user's browser first queries the local cache. If the object is stored on the proxy's disks, the retrieval hit is nearly instantaneous. But caching introduces a new data integrity issue: staleness. The cache must guarantee that the file stored on its local disks hasn't been modified on the distant origin server since it was downloaded. The protocol solves this using the conditional get mechanism. The cache issues an HTTP request to the origin server, but includes an if-modified since header, specifying the exact date the object was originally cached. If the origin server checks its files and sees the object has not changed, it replies with a highly efficient 304 not modified status code. Crucially, this 304 response is sent with a completely empty entity body. The server confirms the data is valid without retransmitting a single byte of the actual file. Conditional gets provide proxy servers with the confidence to serve files at local disk speeds, drastically lowering the overall traffic intensity across the wider internet. While persistent connections, caching, and conditional gets optimize HTTP 1.1, one critical mechanical flaw remained: head-of-line blocking. When pipelining requests over a single TCP connection, data must be sent sequentially. If a massive object, like a high-resolution video, enters the pipeline, it monopolizes the connection. Smaller files, like our 10 JPEGs, become trapped in the queue behind it. To solve this, HTTP2 introduced a framing sublayer, which alters how the application data is formatted before it ever touches the transport layer. Instead of sending large files as continuous data blocks, HTTP2 breaks down standard HTTP messages into independent, binary encoded frames. These frames are then interleaved over the single persistent TCP connection. The large video and the small JPEGs are transmitted concurrently, preventing any one object from monopolizing the link. On the receiving end, the client's framing sublayer catches the interleaved stream, sorts the binary frames, and reconstructs the original, distinct HTTP response messages for the browser. HTTP2 resolves head-of-line blocking by pulling concurrency management out of the heavy, connection-intensive TCP layer and pushing it into this lightweight binary framing process. To meet the demands of the modern web, the original stateless document fetcher had to be surrounded by layers of transport optimization. We minimize RTT delays through persistence, define syntax through strict headers, inject state via cookies, localize traffic through proxy caching, and achieve concurrency with HTTP2 framing. The semantic meaning of HTTP, the methods, the URLs, the 200 OK status codes, operates exactly as it did 30 years ago. What changed are the underlying transport mechanics moving those messages across the wire. The high-speed capability of the applications we use every day relies on this exact architecture, wrapping a rigid, inherently stateless protocol in a highly orchestrated system of transport delivery.